A robotic cargo lander has released a 2-kilogram instrument crate above a rigid test pad. Gravity pulls the crate downward, while empty space provides no upward support. Our simulator must decide what changes when the crate reaches the pad. Which upward force history belongs to a rigid contact model? Should the upward force act during the entire fall, appear only as a brief impact pulse, or produce an impact pulse followed by steady support? Commit to one complete history before the drop begins.
I choose the brief impact pulse. Once the collision has stopped the downward motion, I do not think the floor needs to keep doing anything.
Gravity alone lets the rigid crate pass through the pad, because no rule prevents overlap. An upward force that acts before contact cancels gravity too early, so the crate hovers in empty space. A single impact pulse fixes the velocity for an instant, but gravity immediately starts another fall through the floor. The rigid model needs a state-dependent answer. The reaction is zero while a positive gap separates the bodies. Impact produces a short, large impulse. Continued contact can then produce a sustained reaction that prevents renewed penetration. In a real solid, small deformation spreads the exchange across a short time. The rigid model does not simulate that deformation. It replaces those hidden shape changes with an impulse and a non-penetration constraint. Before we replace contact with a rigid constraint, let us keep a little of the physical story. This object is a deformable spring network made from 15-point masses. Gravity pulls on every mass as the network falls toward a fixed floor. When the bottom point masses meet the floor, what should happen? Should every point receive the same upward force? Should only the overlapping points push back, or should contact be ignored? Choose one complete rule before the network reaches the floor.
I choose the overlapping points. The floor should push on the masses that actually press into it, while the other masses continue to move through the springs.
A soft contact model allows a small overlap, called delta, as a stand-in for material deformation. For point mass I, delta is the positive part of the floor position minus the point's position. The upward contact force combines a stiffness term, which pushes out of the overlap, with a damping term, which resists closing motion. The maximum with zero prevents this contact law from pulling on a separated point. Now the network falls under gravity. Watch the bottom masses compress against the floor, send motion through the springs, and rebound. The amber arrows appear only at points that overlap the floor. The rest of the network is moved by gravity and by its spring connections. This model is more physically plausible than an instant velocity change because it shows a short deformation and a finite force. It has a cost. Increasing the contact stiffness makes the overlap smaller, but it also makes the contact motion faster. The time step must become smaller to resolve that fast motion, so very stiff soft contact can be computationally expensive. The two contact models answer the same physical need in different ways. Soft contact keeps a small deformation and pays for many small time steps. Hard contact forbids overlap, applies an impulse during impact, and solves a constraint during continued contact. The hard model is an efficient approximation, not a claim that real solids are perfectly rigid. A soft contact rule can do more than stop one object at a flat floor. Consider a free sheet made from 391 moving point masses and more than 2,000 spring and damper connections. Gravity pulls every cloth point downward. A sphere waits below the sheet and remains fixed. The sheet begins slightly off-center, so perfect balance cannot hold it in place. Can local contact and limited sliding resistance make the sheet drape around this curved obstacle? Every cloth point receives gravity and the forces from its spring connections. A point receives one additional force only when it enters the sphere's contact layer. Delta means the point's depth inside the sphere. The contact force pushes outward along the sphere's local normal. Its stiffness term grows with depth, and its damping term resists inward motion. A separated point has zero depth, so the sphere exerts no force on it. Contact also resists sliding, but that sideways resistance is capped at 70% of the outward force. The cap prevents this model from supplying unlimited grip. Now release the sheet. Cloth points near the center reach the sphere first, so the first amber arrows appear near the top. The drop began slightly off-center, so the contact patch spreads unevenly instead of relying on perfect symmetry. Outward forces keep points outside the sphere. Limited sliding resistance prevents the whole sheet from slipping cleanly off one side. Spring connections carry each disturbance into neighboring points while the free edges continue to fall. The sheet rebounds slightly, and damping reduces the remaining vibration until a stable drape becomes visible. No animator selected these bends. The calculation moves all 391 point masses. More than 2,000 spring and damper links carry each disturbance across the sheet. Gravity, the springs, the sphere's outward push, and limited sliding resistance create the drape together. In this test, the sphere stays fixed, and the cloth does not collide with itself. This detailed soft model is useful when deformation matters, but it becomes expensive when we try to imitate a nearly rigid crate. A harder contact needs a larger stiffness, and the faster contact motion then needs smaller time steps. A rigid contact model takes a different shortcut. It keeps the crate's shape fixed and solves directly for motion that does not enter the obstacle. We will define that geometric rule next. Contact begins with geometry, not with a guessed upward force. The signed gap, called G, measures separation along the floor normal. A positive gap means separation. A zero gap means touching. The normal component of the contact point velocity tells us whether that gap is closing or opening. The ideal reaction magnitude, called lambda sub n, cannot be negative. The gap cannot be negative either. Their product is zero. These three statements mean that a separated crate has no contact reaction, while a touching crate may receive a compressive reaction. The floor constraint never pulls the crate downward from a distance. In free flight, the gap is positive and the reaction is zero. At impact, the gap reaches zero while the normal velocity is closing, so an impulse changes momentum. At rest, the gap remains zero and a sustained reaction prevents inward acceleration. One geometric rule, therefore, leads to two different timescale responses. The same quantities apply to a corner of a rotating body, except the contact point velocity includes both center motion and rotation. An off-center contact impulse can therefore update the linear and angular ledgers of the same rigid body. The gap and normal velocity tell us when an impact response is allowed, but they do not yet tell us the outgoing velocity. Now the same 2 kilogram crate reaches a fixed floor at 3 meters per second downward. We choose a normal restitution coefficient of 1/4. In this simplified collision law, restitution specifies the rebound speed relative to the incoming normal speed. The crate could stop at the floor. It could rebound upward at 0.75 meters per second, or it could rebound upward at 3 meters per second. Which complete outgoing velocity do you predict? Choose one before we update the momentum ledger.
1/4 sounds like a small bounce, so I predict that the crate leaves at 3/4 of a meter per second upward.
That prediction is correct. The outgoing normal velocity is positive 0.75 meters per second. Changing a 2 kilogram crate from -3 to positive 0.75 requires an upward impulse of 7.5 Newton seconds. This impulse is a finite momentum change concentrated into a short collision interval. After the rebounds die away, the resting question is different. On a stationary horizontal pad, a normal force of 19.6 newtons balances this crate's weight. That is a force maintained through time, not the 7.5 Newton-second impact impulse. Normal force is not automatically equal to weight. If the pad accelerates upward at 2 meters per second squared while carrying the crate, the required normal force is 23.6 newtons. The constraint reaction supplies whatever allowed compressive value enforces the specified contact motion. The normal reaction controls motion perpendicular to the surface. Friction addresses relative motion along the surface. In the simplified Coulomb model, static friction does not automatically equal the friction coefficient times the normal force magnitude. It supplies the amount required for sticking, but only up to that bound. For this crate, the static coefficient is 0.5. As the pad tilts slowly, will sliding begin near 20 degrees, 27 degrees, or 45 degrees? Commit to one angle before the incline moves.
I choose 20 degrees because gravity already has a visible component down the incline at that angle.
At 20 degrees, gravity requests 6.7 newtons of uphill static friction. The available bound is about 9.2 newtons, so friction can supply the requested amount and the crate sticks. It does not spend the unused part of the bound. The threshold occurs when tangent of the incline angle equals 0.5, which is about 26.6 degrees. This is why the 27-degree choice is the closest prediction. At 35 degrees, sticking would require about 11.2 newtons, but the static bound is only about 8.0 newtons. No admissible static friction value can hold the crate, so sliding begins. A kinetic friction model must then replace the sticking rule. The coefficient is an empirical simplification that depends on the surfaces and conditions. It is useful inside its stated model, but it is not a universal microscopic law of materials. One crate creates one contact. 3 1-kilogram crates create a coupled stack. The top contact carries 9.8 newtons. The next contact carries 19.6 newtons. The floor contact carries 29.4 newtons because every lower reaction must support the load above it. If a solver updates each contact once as though the others were fixed, its first answer becomes stale as soon as a neighboring reaction changes a body's velocity. The result can depend on update order, and the stack may compress, separate, or jitter numerically. A coupled solve, or a converged iterative approximation, lets information propagate through the contact network. The final reactions satisfy all 3 non-penetration conditions together. This is why contact resolution is a system problem rather than a collection of unrelated upward arrows. A body that crosses a thin surface between sampled times is tunneling, which may require smaller steps or continuous collision detection. Repeated overcorrection can produce jitter. A biased update can inject energy. An unconverged sequential solve can remain order-dependent. Each symptom points to a different numerical repair. Contact is local, but even local constraints become coupled in a stack. The next episode changes the interaction law. When every body attracts every other body through gravity, 10,000 bodies create almost 50 million unordered pairs. The physics stays compact while the organization of the computation becomes the central problem.